this computer. All right. Hey guys, we're gonna start now, I think, and Nikunj is going to be leading us off with linear stability analysis today. So he can introduce himself and however he wants to do it.
These two folks already know me.
Oh wait, yeah, they already know you, but also my computer is muted, so even if they've been talking, we definitely can't hear them. I'm so sorry, I had you all muted. Yeah, okay.
So today I thought I'd cover linear stability analysis. And so the basic idea is that, let's say, like last like 3 weeks ago, Carly taught us differential equations, and you would have quickly realized solving differential equations is really hard. And so linear stability analysis is a way of sort of trying to get something out of differential equations without solving them. Okay, and so I'm going to talk about what it helps us to do with and how to do that. Okay, cool. So let us think there's a population of giant tortoise like in Galapagos, one of the islands of Galapagos, and it's like we introduce some individuals in that on that island, and we want to understand is how does the population of those tortoise change over time. Okay, like one way in which we sort of describe change is by writing an equation about how does the rate of change of population happens. Okay, and the simplest way of sort of thinking about it, let's say you have n of t gives you is the time dependent population of tortoise. Okay, and I say what I want to say is find is the rate at which this population change over time. Okay, if I'm like if tortoise consume grass and then the grass is abundant, so what I would say is that this tortoise grows like the growth, the rate of change should be first proportional to the number of tortoise in the island, because you cannot have like 100 rate of change, like one can go to 2, 2 can go to 4, and so it should be somehow first should be some proportional to n, and then you multiply it by something called as per capita growth rate, which is R, which tells you is the rate of change of per unit, like the per capita change in per capita rate of growth of those tortoise. Okay, and so this is like a very like famous ecology model in like which is taught in introductory evolutionary ecology courses. This is the exponential growth model. Okay, so the way to sort of think about it is that let's say you have like let's say you have draw this graph. On graph you say on y-axis you plot dn by dt, and on the x-axis you say n. Okay, so from this you can say that dn by dt is this line which has a slope r, right? So let's say at time t equals to 0, you introduce a population like some number of, let's say 10 tortoise in this place on the island. Okay, and then what you will see is at n naught, what is the rate of change? You know, like is it positive, negative? Yes. So if it is positive, this means that the population has to increase, right? So at small like so the population will start increasing in this direction. So let's say the population increased by 5 tortoise. Okay, so then we are somewhere here. What is the rate of change of population here?
Still positive.
Still positive. And so what you see is that it kind of go on increasing over time, and so it's sort of increasing increasing over time. And so this this is a graphical representation of the whole problem. Like I haven't done any, I haven't really solved this mathematical equation, but still I'm sort of somehow able to understand how the population will change even without putting any numbers to it. Okay, this equation is actually very easy to solve. So the way to solve this is like I think Carly taught us this last time. You say you take dt on the other side and you integrate on both sides. So let's say at t equals to 0, the population was n naught, and you want to find it at time t equals to t, what would be the population at this thing. Okay, so you can sort of integrate this. The right hand side would be RT, and the left hand side would be ln of n of t by n naught. Okay, and then you exponentiate both sides, you get n of t equals to n naught. You get n naught e power RT. Okay, and so you can see, as long as this R is positive, the per capita growth rate is positive, the population will increase exponentially. Okay. Oh, you have chili. It's okay. So does any of this doesn't make sense? Just, or does this make sense? And we're like, oh, this is just too trivial.
A pen or a pencil?
I also have something if you want, but okay, good.
Sorry, it wasn't
Good. Is this like this portion clear? Okay, cool. Can you tell me what is the limitation of an exponential model, or like why would this not work for a tortoise? Like, elaborate. Yes, there will be some limiting factor. Like it's like population cannot increase like indefinitely, right? And so what we do is we try to make this model a bit more realistic. And okay, I'm going to erase this. But remember this equation, kind of. This is important, and we'll sort of circle back this like throughout like next 2 weeks. Okay. So the next way sort of what we do is, instead of having, so the problem basically here is that R is a constant here. Which means that, let's say, if it doesn't matter whether the population is 100 million or 10, all tortoise produce at a rate R. Okay, which is not true. Like once you reach like a certain limit, let's say if the tortoise population reaches something like 2,000 individuals on the island, they'll start self-limiting each other because of constraint on resources, or some these resources could be grass, could be breeding sites, it could be many, it could just be space, right? And so one way of sort of resolving this issue is you replace R by something that limits R when the population is very high. So, like I say, when population is very low, what would this term be? This thing. Like when population is very low, what would this be? K is very large, I guess. Huh? Exactly. It will be close to 1. And so you multiply 1 into R, you will get R. So you get exponential model again when the population is low, which kind of makes sense. But let's say the population is very large and it's actually near K. What would this growth rate be? Yes. So this means that this somehow encapsulates the idea that there are constraints on resources, and that limits the population growth rate. Okay. So what I basically do is replace here R with R into 1 minus n into 1 minus n by k and n. Okay. Now I want to understand is that how does the population change on an island if I introduce, like, say, 10 tortoises? Okay. First thing is, this equation is not really easy to solve. Like, it is solvable, but like it's not as easy as exponential model. Okay. So the way we go about it, first we do is again graphical analysis to get some intuition. Okay. So let's say you have a rate of change. You say that the rate of change of population is given by dn by dt, and you plot it against n. Okay. So can somebody tell me what would be the shape of this part? Yes. It will be kind of an inverted parabola, right? And it's inverted parabola because r is greater than 0. If r was less than 0, that actually would be the opposite way. Okay. So now let's say we introduce some population of tortoise here, n naught. In which direction would the population change? Will it increase or will it decrease? Why? Not the slope is up, it's because dn by dt is greater than 0. Okay. So because dn by dt is 0, it kind of goes here. So let's say we have let's say this intersects at carrying capacity, and so even here we'll sort of go towards k. Let's say somehow I exceed k, or somehow exceed k. Then what would happen? Would the population increase or decrease?
Decrease.
And that's because yes, the growth rate is less than 0, and so it will decrease. So what you can see is that like the population basically will converge to the carrying capacity of the system. Okay, and this introduces the notion of equilibrium points. So equilibrium points are places where the population do not change. Okay, and can you figure out what are the equilibriums in this situation? Yes, 0 is important thing. Like I didn't talk about it. Like so, k and also intersect at k n equals to k. Your dn by dt is 0, and so is dn by dt equals to 0 at n equals to 0, or when the population is extinct. Which makes sense. If an island doesn't have a tortoise, then there will be no tortoise after like 10 years too. Like this is not possible. Okay, but it is an unstable point. Meaning that if I introduce a few number of individuals, then they will take over the population. Okay. So this introduces, I will introduce two things. One is the notion of equilibrium points. The equilibrium points are like equilibrium points are places where dn by dt equals to 0. Okay. Then I will introduce the notion of stability. Okay. So I've defined that an equilibrium point can be two things. It can be stable and it can be unstable. So stable and unstable. So what characteristics define an unstable and stable equilibrium point based on what we discussed? Like how would we want to evaluate whether a point is stable or not in basically in this graphical case? Yes. Yes, this is like the central notion in linear stability analysis. Basically, if you put up the system around an equilibrium point, if it goes towards it, it is stable. If it goes away from it, it is unstable. Okay, I want to say this one more time because this is going to be the case even when we do matrix differential equations. Like a point is stable if you put like a equilibrium point is stable if you sort of go a little bit far away from it and just let it evolve, the dynamical system evolve, it will go towards the equilibrium point again. So that's a stable equilibrium point. If it goes away from it, it is an unstable equilibrium point. So in this case, if you somewhere here less than carrying capacity but greater than 0, you will go away from 0 and towards k. And so that's why k is stable, or carrying capacity is stable, and extinction is unstable equilibrium. Okay. Am I cool? Okay. Let's complicate things a bit more. So let us say these giant tortoise population, when they are low in density, they really can't find mates. Like they need a female partner to sort of produce. And so what this means is that when you are low, your growth rate should be negative, right? But this model tells you that's not the case, right? This is a reasonable model for an asexual population like a plant, right? Or like a eel or bus, or something like that. But for tortoise, this may not be a good model. So what we want to do is we want to introduce negative density dependence at low density. It's just a way of saying that the population should decrease when there are fewer number of individuals. Okay, does this make sense? This is what we call as alley effect in ecology. Okay, so the way we model alley effect is we just say that we sort of multiply this growth rate, the rate of change of population, by this new term n minus a, where we say that this a is a threshold that the population has to cross before tortoise kind of start finding mates and the growth rate is actually positive. Okay, cool. So let us modify this graph to sort of account for that. So It's fine. So again, you have carrying capacity. The curve should hit, like the curve should intersect at carrying capacity. Where else should this curve intersect on x-axis? Or where would the rate of change of population is 0?
At A.
Yes, and
At 0.
yes. So here, here, and here. And if you draw the graph, it will basically be like this. Okay, cool. Would the population increase or decrease here? Would the population increase, decrease here? Would the population increase or decrease here? Yes. So now actually 0 is a stable point. So if you see that if you are anywhere in the neighborhood of this place, you're going back to 0. Okay. And if you're in here, like you're going to K. So A is an unstable equilibrium point. 0 and K are stable equilibrium points. Okay. And we haven't solved the equation yet, right? And this is the magic power of linear stability analysis, is sometimes you just don't have to solve differential equations. You can just look at them and then argue whether what should in the long run, what should happen to the system. Cool. Okay. So this is great. Like you can plot graphs and then you can do such stuff. But what if you just can't? It's a complicated growth function. It is not a very simple function like this is not like a simple function which you can factorize and stuff like that. How do you approach like finding first like what are the equilibrium points and calculating their stability? Like this is the topic of what I'm going to do today. But in the one thing that I kind of wanted to stress was the notion of stability and unstable and stable equilibrium points. Stable, you go towards that point. Unstable, you move away from that. And I'll basically explore this point mathematically. Okay. Good. So whatever I'm going to like talk next would be hard for some people and trivial for some other people. So whenever it is hard, stop me and ask me questions, okay? Because for me, I have very bad understanding of what people know and what people don't know. Okay, so let us say like this is again I'm trying to model the population dynamics of a tortoise or your favorite coral or plant species. Like we just pick it up, okay, and we say that the population of that animal or plant, the rate of change can be described through this function called f of n. Okay. We have already seen 3 functional forms of f of n. One was the exponential, one was logistic growth rate, the third one was Allen effect model. Okay. So what we want to do is we first want to find stable equilibrium points of this system. Okay. How do we do that? Yes. So what would that imply? Yes. So basically that would imply is Fn is 0. And I'm going to call those particular values of n where Fn is 0 as n stars. Okay. So these are equilibrium points. So I'm going to denote equilibrium points as n stars. In the rest of the presentation, whenever there's a star, that is by definition an equilibrium point. Okay. Now, I define a variable called delta n of t as this, which is saying that this is the population at any given point of time, and this is the population at equilibrium point. So I define a variable delta n of t which tracks how does the deviation of the population, what is the deviation of the population from equilibrium point. Okay. What if n star is stable? What should be this? What should happen to delta n as time increases? Yes. Right? It should go to 0. So delta n should decrease, or the absolute value of it should decrease as delta t increases. Okay. This is stable point. Okay. What should happen if it's an unstable point? it should increase, right? So we've just basically turned that qualitative argument into a more quantitative argument of what we're trying to do here. Okay. Delta n should increase as delta t increases, gives you an unstable point. Okay. Cool. I'm going to rub this and then now interesting stuff starts happening. Okay. How many of you know what is a Taylor expansion? Taylor expansion. Okay. This is the best part of things I can teach. It's like Taylor expansion is the most important math concept in applied math. Okay, cool. So let's say I define this delta n equals to n minus n star, right? I differentiate both sides. So this is a variable. This depends on time, and this is a variable that depends on time. But this is a constant. Okay. So let's say I say d by dt of delta n equals to dn by dt minus dn star by dt. Okay. What is dn star by dt? Why? Cool. Not many people get this. It's actually a constant because by definition I wrote like equilibrium points are like one thing on the graph, right? Okay, I messed this up when I was first learning it, so I think this is not trivial. Okay. So this will go to 0. And okay, then what is dn by dt? Dn by dt is f of n of okay. So my rate of change of population from an equilibrium point is basically f of n. Okay, cool. Now what I want to do is there is something called as Taylor expansions. Okay, I'm going to first present what a Taylor expansion is, and then I'm going to tell you why are we using it. Okay, so if you don't understand why am I writing some stuff, it's okay. Just wait for 2 minutes and then it will become clear. Okay, so let us say you have a graph like this, some function. It doesn't necessarily, okay, let's say you have a function f of x, which goes like this, okay, and you said that I said that this is a point on this function called x star. Okay, so if I ask you what, let's say you don't know the function, but you just know what would be your best guess of the function if you don't know anything but just this thing? Like if, like let's say, what would be the approximation? How would we approximate the? Let's say you want to approximate what would be the values of the function around x star. Okay, what would be your best guess?
Yeah.
No, the best guess would be actually the f of x star itself.
Oh.
Right? You will be like, okay, all the points should be, because it's a continuous function, no, all the points should be close by. So like I'll say that any point that is nearby, it should be down to what f of x star. Okay. So the next best approximation is you say, okay, I know that it is f of x star, but what if I just add a slight line here and be like, okay, I know it's x star, but I can do better by interpolating using a linear function, right? Then what I can do is, if I'm becoming much more greedy, then I can say, okay, and let me include a curvature also, and then I'll approximate a part of curvature, like a parabola on it somewhat. And so what you do is, what I'm trying to say is that you can expand the function value at a particular point, or at least in the neighborhood, by fitting larger polynomials like x, x squared, x cubed, and so on and so forth. Okay. And so mathematically, let's say if I'm given a function x, and I want to evaluate the value of the function around the neighborhood of x star, I can write it as follows. Okay. Space to write this as a bit here. F of x equals to f of x star plus df by dx at x equals to x star x minus x star x, 32 and 28, x equals to x star, x equals to x star, square, 0 factorial. Okay. And so on, so like, and then I'll just keep on writing like this. Can you just guess the general form? The general form is basically this. It's summation f of n, meaning f dash, meaning we're taking the nth derivative. Or should write this. N 1 by factorial. This is the general form, and n goes from 0 to infinity. This is the drawn out version of it. I'm never going to use this because it just is ugly. But basically that's the linear expansion. Okay, so let us just go term by term. So this is f of x star is like always like it's just evaluating the function at x star. This is saying that you calculate the slope of the function at x star and multiply it by how much it deviates from x star. Okay. This is saying that if you want to fit a parabola at that point, you take the double derivative at x star and then multiply it by x minus x squared. Okay. So far so good? Okay, cool. So let us say, oh, I want to expand this, and I'll expand this around the equilibrium point. Okay, the reason why we want to do it around the equilibrium point is because of the previous notion that I told you. Like when something is stable, if you are near the equilibrium point and if you perturb a bit, you should come back to it. That is why tail expansions are really good, because it expands the function around an equilibrium point. Okay, and that is very useful. You will see how that can be. So let us say, okay, so can somebody volunteer? So what would this be if I substitute expanded it n star? Anybody? So let's say if I want to expand f of n at n star using Taylor expansion, what would that be? Yes. Okay. Let's say I can do it n here, n here, n, 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 and so on and so forth. Right? What is this guy? What is this thing? Exactly. It's delta n. Okay. What is this? Okay, delta n square. Cool. This is great. Okay. Now, a very basic question, but which is not trivial so much, is let's say if you have a very small number, if you take square of that, whether is that number big or small than the number is even smaller. So let's say you have 0.1, you take square of it. It is the square of 0.1 is 0.01, which means it is decreasing. Okay, so if I'm saying this delta n is small, which by definition I'm because I'm in the neighborhood of n star, what would be delta n square? It will be much smaller quantity, right? Like extremely small quantity. And I said it can be arbitrarily close to the equilibrium point. So this would be really small quantity. And so would be the higher powers of delta n. So what I can do is I can first of all remove all of them. I'm like they are all basically 0. Okay. What is f of n star?
N star?
Yeah. What? Huh?
0.
It's 0 because it's an equilibrium point, right? It's basically it's because I said that when you're at an equilibrium point, dn by dt should be 0, which means f of n should be 0, or f of n star should be 0, which means this should also be 0. Okay. So the only term or the leading term or the main thing that is left out is this quantity. Okay. So I can approximate f of n star, f of n as follows. Does this make sense? Right? This is a constant, right? Because it's a derivative at an equilibrium point. I'm going to call this constant as lambda. So what I get is a very simple expression of f of n around equilibrium point. It is basically lambda times delta n, where lambda is the first derivative of the growth function at the equilibrium point. Okay. Does this make sense? Lambda is the first derivative of f with respect to n at n star. I'm assuming what you know derivatives. Okay, cool. So now I can write this equals to lambda delta. Okay. So now I erase these middle steps which I wrote. Okay. And then just basically write. Okay. Can you solve this equation? Right? We can do that. This was the first equation I solved when I began sort of talking about it. So if you solve this equation, you will get this. Delta n equals to delta n naught, which is the initial deviation e power lambda t. Okay. Now by looking at this, tell me when would delta, so this is positive, delta n is positive, okay. When would delta n go to 0 if time increases? What should happen in this equation such that delta n goes to 0 as time increases? Huh? Yes, it has to be a stable equilibrium first. Okay, but what should that correspond to here? What do you have to assume before that can happen? Like, okay, can you think about what should be the sign of lambda? Yes. Can you see that? Why should that be? So if you can't see that, you have to tell me. Like I won't. You can't. Huh?
Yes.
How? Can explain. Okay. So let's say this lambda is positive 2. Okay. So it's like 2t. If you draw the graph of 2t, e power 2t, it will increase with time. This is e power 2t versus time, and this will sort of increase. Okay, so this is put t equals to 1, it is e square, t equals to 2, it is e power 4, and that will increase. What if you put minus 2t? Then actually this graph will decrease. So this exponent basically tells is whether the graph is going to increase, or like this thing is going to increase or decrease. So for a point to be stable, we can say is that if lambda is greater than 0, the equilibrium point is unstable. And if lambda is less than 0, the equilibrium point is stable. Yes. Oh, I solved this equation to get this. Oh, okay. So let's say you have d delta n equals to lambda delta n times dt, right? I can do this. I can just bring, okay. Then I can integrate on both sides. Okay. So I say that at time t equals to 0, I am delta n not away from the equilibrium point, and at time t equals to t, I am delta n away from the equilibrium point. And then you sort of integrate, this will be ln of delta n by delta n naught, and this will be lambda, oh sorry, this is, sorry, and that should be lambda t. Okay, and then you sort of take exponent of both sides, you get this. Okay, cool. So now we're going to analyze. Okay, first I'm going to recap what I just said, and then we're going to analyze this logistic model using this math. Okay, and see, I'm basically going to recover whatever I said before. Okay, cool. Step one, like the first thing that you do is you equate f of n star equals to 0. Okay, from that you get equilibrium points. Okay, then you evaluate lambda, and where lambda is this, is the derivative of that growth function at that equilibrium point. Okay, if that derivative is less than 0, then that equilibrium point is stable. If that is greater than 0, then the equilibrium point is unstable. And then you do it for all equilibrium points, not just one, and every equilibrium point. Okay, good. So now let's do an example.
And once you kind of have one equilibrium point, can you just kind of like bounce between to figure out stability?
You can, yeah, because equilibrium points occur always in conjugate pairs, unless you have a bifurcation point. In the bifurcation point, what happens is the second derivative is also 0. So the first derivative is 0, so the second derivative is non-zero. If you know what I mean, you know. Yeah. So yeah, but you can do that. Yes, like
I was right, because you just said you need to check them all.
analytically, yes, analytically you need to. And also, like when you have higher dimensional spaces, then there is no order because you can go around an equilibrium point in the second dimension, and then you have to actually check all the equilibrium points.
But for something really simple.
Yeah, something really simple you can. Yes. Cool. Okay. So I pick dn by dt equals to r into n into 1 minus n by k. Okay. Let's solve what is dn by dt equals to 2. So when is dn by dt equals to 0? We've done this. Right? Does this make sense? Okay. Now what we have to do is we have to calculate the derivative of this and evaluate at both of these equilibrium points. What is the derivative of r into 1 minus n with respect to n? Meaning this is, let's say this is f of n. What is df by dn?
R minus 2n. Okay.
Yes. So this is basically r into n minus r times n square by k. Like I just took n inside, and if you take the derivative, of this whole thing, that derivative would be r minus 2r n by k. Right? So the derivative of is this. Good. Next thing is we have to evaluate this derivative at the equilibrium point. So let's pick 0 as our first equilibrium point. So at n star equals to, at n star equals to 0, what is df by df? Just r, right? Because you substitute n equals to 0, this whole thing will be 0, and then you just have an r. You're saying that r minus 2r times 0 by k, this thing goes to 0, and you have r. So if your per capita growth rate is positive, your first derivative with respect to n is also positive. So it's an unstable equilibrium point, because that's what we said. Like if the first derivative is greater than 0, it's unstable. Okay. What would happen when n star equals to k? What is the value of this derivative?
R minus 2R.
R minus 2R, which is minus R.
Minus R.
Yes. So this will be P not k by n equals to R minus 2R k by k. K cancels, and then R minus 2R is minus R. So if your per capita growth rate is positive, minus R has to be negative, which means this is a stable equilibrium point. Okay. So we just did this whole thing graphically as well, right? But now we've done this more mathematically, and we've talked about how like this. Then this is the linear stability analysis when you have one dynamical variable. Okay. So the next thing I want you folks to do is practice this thing. Good. Now, however you want to do, calculate the equilibrium points and the stability for an alley effect model, and check that A is unstable and K and 0 are stable equilibrium points. That we have time. Don't look at this.
Messy.
No,
Am I just like not
this is the
messy?
derivative. This is the derivative. Use the product. Huh?
But then like to get where it started with 0, do you plug it into the quadratic equation or is it supposed to reduce more?
I don't reduce this. I just start putting stuff here because it's so I start putting here if n is 0 this term and I don't have to evaluate. So this is all 0. So and this
Oh, I
is
just didn't fucking know that.
I was trying to factor it out. So I think okay, this is 0. This will be 0. This will be a minus a times r a.
And A is strictly less than. Right?
Yeah. I think so. I might have messed up this equation. It could be a minus m two.
It's this is not. I don't know. If that's right. I think that's right. Though. Oh shit, no, it's not. Oh yeah, yes. Sorry. Okay. Sorry, I think
Let me see. Ali, sure.
One.
Yeah, it's good. Something wrong. Okay.
Oh, yeah. That's only, it should be on two. Less than eight, it's okay. This
Okay. Did you folks get this thing? So this is the final thing.
Oh, yeah.
Yeah.
How did you know? Maybe it's better.
I think it's mostly about taking derivative, like using the chain rule to take derivative and not expand.
I did
That would
that.
make
That would
more
make
sense.
sense.
Because that's it. The reason I did it like because I took chain rule. If I substitute n equals to 0, this whole term is 0, so I don't have to evaluate it. And only this terms need to evaluate. And when n equals to k, this goes to 0, this goes to 0, and only these two things leave out. So it's just
Yeah, I got it.
okay. The idea is, huh? You got them all? Correct.
Oh, delightful.
Sunishka gets a candy. Okay. The point of doing all of this was to make you familiar with what we're trying to do. We're first trying to find equilibrium points, then take derivative and substitute those equilibrium points back in the equation, and voila, you get stability and equilibrium points. Now you can try to understand like how your population dynamics, like how where the population will equilibrate and whether there are equilibrium points or not. Okay, so I'm going to include like maybe spend 5 more minutes to include one more complexity. And then we are going to go next week, and we're going to introduce matrices, what Emily taught us, like into this thing. And can we do 5 minutes, 5 more minutes?
Yeah.
Okay, cool. So going back to the tortoise thing. Okay, so in tortoise thing, we kind of assumed that the resources are finite, but they get kind of replenished every like every year, meaning that I have only like, let's say 10 kgs of grass per meter square, but somehow it gets replenished by itself every year. And so it remains constant, but it is there. But that's not true. Like plant population also sort of gets regulated by the population of tortoise. So what we want to do is we want to write, like if you want to try to understand population dynamics of tortoise, we kind of want to model the grass dynamics as well. Okay. Does that make sense? Like this, these are like classical predator prey models and stuff like that. So let us say that I have a plant population and I say this is changes as a function of time as this dp by dt. Okay. So, and that plant population grows exponentially when the plant is rare. Okay. And it is regulated by the tortoise population. T times P. Okay. This is important. Why am I written is a product of T times P. When there are no tortoise, there is no regulation. Okay. And when there is no plants, again there is no regulation. Because there are no plants, you cannot further decrease plants. Okay. So that's why it's a product of those two things. Okay. Then similarly, I can write the tortoise populations as CTP, meaning that whatever they consume gets converted into the tortoise biomass, and that increases exponentially. And then tortoises die because of old age. This D is not to be confused with this D. This D is actually a parameter, so I'm going to actually replace it with something else. E of T. Okay. If you solve these equations on a computer, you'll see this thing. This thing. If you plot tortoise, you get this, and if you get plant, you will get they're kind of out of sync. You'll see when a tortoise population increases, the plant population is low, and plant population is high, plant population is low. That's like a characteristic of like consumer resource interactions cycles. Okay, so the goal of this is again to calculate equilibrium points and find whether those equilibrium points are stable or not. There are many interesting things happen here, like which didn't happen in a 1D case. And so in the next week, what I'm going to show is that we can understand how population dynamics happen using the same concepts of stability and like this per topic cross equilibrium point, and see how it sort of comes back to the equilibrium point. But we'll use matrices now because we want to track two things now instead of one. And matrices are a very good way of tracking those things, and I'll show you how. Cool.
By next week, you mean literally?
Or well, not next week, but whatever.
I guess we do it 2 weeks from now. We're on,
Two
yeah,
weeks
it's
from
now.
now.
I know, I wasn't sure if we were recently.
Oh, it's 2 weeks from now.
No.
Thanksgiving?
We can do next week means like next time.
Why don't we, let me look at the calendar. Well,
Yeah, 2 weeks from now is literally Thanksgiving.
let's do this the week we come back from Thanksgiving. So
The
we can, I
first
guess,
week
we
of
can just go, would you rather do this 1 week from now or 3 weeks from now?
It would get us back on schedule and give us time for numerical analysis.
If we do it next week?
If we do it next week, we'll be back on.
Yeah, I guess, well, this is also a discussion for, initially our last meeting this semester is going to be numerical analysis of systems. We could also do a reading group instead of a math group with a classic ODE systems paper, which I also think would be helpful.
Yeah.
I guess it's not on know about it, but let's decide on, so let's meet. Next week? I mean, you're the one leading it.
Yeah,
so-
I don't have a problem. Like whenever you want.
Yeah, well, here's our new schedule. We're gonna meet next week. We'll meet the first week of December and we'll call it the semester and we'll start in January, I think, with stats based.
Cool.
Yeah. Cool.
Hi Shinji, I'm going to end this thing.
Yeah, let's end it.
I should also stop.
Yeah, stop.
Well, nice to see you guys.